This talk is on aspect ratio. It shows us the shape of a rectangle. You also use that term for other shapes, but primarily rectangles. It's the ratio of the length to the width. You're familiar with this term whether you remember it or not because you see it on televisions and on monitors.
Amir Vasquez, if you're the building, come to the office. Amir Vasquez to the office.
Here you can see how it plays out on the various incarnations of television. Here's the oldest one from the early 50s through the early 2000s. All televisions were in the aspect ratio of 4:3, which means they're all similar, so wherever the image was produced, it would fit into whatever size screen there was, be it the tiniest original iPod screen, which was 4:3, to the bigger ones, which got up to 22, 24 inches. They thought that was really big then. Our current TVs are no longer dependent on the cathode ray tube and can get much larger. They are now in the aspect ratio 16:9, which many filmmakers think is a more pleasing shape to be able to get the types of things they usually put on TV. Movies are even longer and narrower. Most of them are 12:5, although that is not standardized. This was just Black Friday and Cyber Monday. So we saw a lot of TV sales. When your TV sales are, the salesman lists only the diagonal in TV sales. Why? Why only the diagonal? The most useful, I think, is the length, because that tells you how big of a table you got to have to put it on, or perhaps the height, the width, because that tells you what can go above it. But the diagonal really doesn't tell you very much. So why do they do that? I think the reason they do that is because the diagonal, being the hypotenuse of the triangle, is always the longest dimension. Any one of them would still tell you how big the TV was because they're all in the same aspect ratio. But the diagonal is the one they choose because it's longest and makes the TV sound biggest. That's marketing for you. Here's some illustrations of how this works out on going from one aspect ratio to another. So when you have an image in an aspect ratio and a TV or monitor in a different aspect ratio, it won't fill the screen properly. For example, this is an old TV screen, which is aspect ratio of 4:3, with a new TV image 16:9 projected onto it. You see that it doesn't fill it. There's space at the top and the bottom. Here is from when the new TVs were new. If he's watching Gilligan's Island or I Love Lucy or something like that, this is what it'll look like. Because when it was originally made, this is all the picture that they made. It was only at the aspect ratio 4:3, and so that can't fill up the current screen. So if you're watching Gilligan's Island now, there's going to be a bar on either side because nothing was filmed to go there. The worst one of these, I think, was trying to watch a movie on an old TV screen. Old TV screen, 4:3 aspect ratio, typical movie, 12:5. Notice that the bars are quite large. So they didn't usually show it this way because so much of it, the TV wasn't that big anyway, and so much of it is not the image that you want. Typically what they'd do is just cut off the sides and you only saw the middle of the movie, which was less than wonderful, but better than nothing. Let's work on a problem here. Using a ratio to find a dimension. You're planning to paint a mural on a rectangular wall. You know that the perimeter of the wall is 484 feet and the ratio of its length to its width is 9:2. Find the area of the wall. There's at least two ways to do this. Let's look at the information you have. You know that the ratio of length to width is 9:2. You also know that the perimeter is 484 and that for a rectangle, the perimeter is 2 lengths plus 2 widths. We've got two equations. We've got two unknowns. This can be solved as a system, you all being proud graduates of Algebra 1. Come over here to isolate one of the variables. It looks like W can go, that I'll isolate the L. That'll give me length equals 9W over 2. Now that length is isolated, L is isolated, I can plug it in and put everything else around it. The 2's cancel, and we get W equals 44. We substitute that back into the original equation. We get that length is 198. Multiply those two to answer the problem to get the area of the wall. Another way to do it, which is probably better for this particular circumstance, is treating the ratio more directly. Let's look at how we make equivalent fractions. You remember doing that in elementary school. 9 over 2, I can make the equivalent fraction 18 over 4 by multiplying both the numerator and the denominator by 2. In other words, by multiplying 2 over 2. Multiply by 1, 2 over 2. Or I can multiply by 3 over 3, the numerator and the denominator both by 3. That'll give me 27 over 6. I can do them both by 4. That'll give me 36 over 8. I can just keep doing this. I know from the previous problem I want the bottom to be 44, but I'd really like a better way to solve it algebraically so I don't have to just guess and check all the time. Look back how you form these equivalent fractions. What you do each time is multiply by 1 in the form of the scale factor. So we can show it as 9x over 2x. I've multiplied both the numerator and the denominator by x. X over x, of course, is 1. So here we have the scale factor represented as x. Well, how can I use that? Here is the length. Here is the width. So I can represent the length as 9x, the width as 2x. I'll put it back into my perimeter formula that we've just used. 2 length plus 2 width. That'll be 2 times 9x for the length plus 2 times 2x for the width. Is 22x, or x, I'm sorry, is that right? Yeah, 22x, or x equals 22. Notice that this is the scale factor. This is not the width or the length of the rectangle. To be able to get that, I'll need to do 9 times x for the length, which is 198, what we got before, and for the width, 2 times x, which is 44, which is the width and the length that we got previously. So we get the same answer either way that we do it. This way, however, is probably more helpful, more instructive for what we're doing here. So we'll go with that way, although the other way works just fine. Let's look at another example, how we can use the ratios. This is an extended ratio. You've probably not seen extended ratio or heard that term before. This is a very simple problem. We'll work through it to show how we're doing it. The picture already tells us everything we need to know. The measurements of the angles are in the extended ratio of 1 to 2 to 3. We can represent the angles as they're represented here as x, 2x, and 3x. Of course, when you reduce that, all the x's go, and it's 1, 2, 3 is the ratio, which is the one that we need. So the angles are 1x plus 2x plus 3x, and we know from the triangle sum theorem that the sum of the angles of the triangle are 180 degrees. So we have that the scale factor, which is what we've just gotten now, is 30. So 1 times 30 is 30, 2 times 30 is 60, 3 times 30 is 90. So the three angles are 30, 60, and 90. I'm going to try a few problems here, please. if you would copy these in your cipher. You need to copy the problem because otherwise when you come back, you won't know what you had. So go ahead and copy these problems, and I'll display the answers for you. You might want to pause here. Okay, here are the answers to the first problem. Make sure you know how to do it. And here are the answers to the second and third problem and how to work them out. Make sure you're understanding how to work them out. If you don't, go back and check it to be sure.